Okay, so just a little bit of a reminder for the big points from last week. We had sets of data. One of the things we did was we summarized them numerically with numbers. And we had measures of center, which were our mean and our median. And we also had a mode in there and a mid-range. I didn't ask for any of those here. The main reason I didn't ask for a mode is with a very small set like this, usually there isn't a mode. If you have a larger set of numbers, of course the mode is the most common number, and so whichever number occurs the most often is the mode. With a small set, usually there isn't any numbers that are repeated. So let's start with the mean and the median. How do we find the mean? Well, it's two steps. What's the first step? Add them up. So we're going to take 7 plus 12 plus 14 plus 15 plus 17 plus 25. And what do we get? 90? 90. Step 2 then is to divide by n. And what is n? The number of items in our list. And n in this case is 6. So we divide by 6. 90 divided by 6 is 15. Our mean is 15. The median is also a two-step process. Step 1 is to put them in order. Smallest to largest. It's already in order from smallest to largest. Step 2 then is to find its position. And to find its position, it's always n times 0.5 or 0.5 times n. So in this case, it's 0.5 times 6, which is 3. Now remember, there's two possibilities. Either we get a decimal, like 3.5 or 8.5 or whatever. When we got a decimal, what did we do? We would round up. If we had 6.5, we'd round up to 7, which meant the 7th number in the list was the median. If we got a whole number like 3, what did that tell us? Nope, that if we get a whole number, it's actually between that one and the next one. So it's between the 3rd and the 4th number. Remember, what we get here is telling us how many numbers come before the median. So if we got a 6.5, it was telling us there's 6.5 numbers that come before the median. The median would be the 7th number. Here it's telling us that there's 3 numbers that come before the median. The median is between the 3rd and the 4th, that one and the next number. So between the 3rd and the 4th, we've got 1, 2, 3, 4, 5, 6. It's between the 14 and the 15. We're going to add those together. We're going to average them together, basically. 14 plus 15 divided by 2 is 14.5. Bit of warning there, by the way. When you do that addition, make sure you hit equals before you hit divided by 2. Otherwise, your calculator will divide the 15 by 2 to get 7.5 and add it to the 14, tell you 21.5, which is way off. Same up here with the mean, by the way. Make sure that when you're adding, you hit equals before you divide. The range. How do we find the range? Is the maximum or the largest number minus the smallest number or the minimum. So what do we do here? What's the largest number? 25. What's the smallest number? 7. So that gives us a range of 18. That one's not so bad. The next one's the long one. Standard deviation is a 6-step process. What is step 1? Find the mean. We've already done that. The mean is 15. What is step 2? Step 2 is to subtract the mean from each number. So we're going to take 7 and subtract 15, 12 and subtract 15, 14 and subtract 15. 15 and subtract 15. 17 and subtract 15. And is it 25? Yeah, 25 and subtract 15. So that's going to give us 7 minus 15 is negative 8. 12 minus 15 is negative 3. 14 minus 15 is negative 1. 15 minus 15, 0. 17 minus 15 is 2. And 25 minus 15 is 10. Now, if we wanted to, as we've said before, we could double check here. If we added those all up, what should they add up to? 0. They should add up to 0. At this point, after we've subtracted the mean from each, that's a way to double check. If they don't add up to 0, we did something wrong. Chances are our mean's probably wrong. So now what is step 3? Square them. So negative 8 squared is 64. Negative 3 squared is 9. Negative 1 squared is 1. 0 squared, 0. 2 squared, 4. And 10 squared is 100. So we can add them all up. 64 plus 9 is 73, plus 1 is 74, 78, 178. Step 4, by the way, was to sum them up or add them up. What is step 5? Perfect. Divide by n minus 1. N equals 6, so we're going to divide by 5. 178 divided by 5 is 35.6. Since n was 6, 6 minus 1 is 5, so we divided by 5. If you were asked, this number, by the way, is the variance. Stop right there, that's the variance. What is our final step for finding the standard deviation? Square root. Square root of 35.6, approximately 5.9. .966, so we'll go 5.97. Any questions? How many of you feel really good about finding those 4 quantities from a set of data? Nobody feels real good? A couple of you? Okay. Anybody feel really overwhelmed by trying to find those 4 numbers, those 4 quantities? Well, that's good at least. As I will tell you that all 4 of those will be on the test. Oh, by the way, for those of you that only have night classes, coming up 3 weeks from tonight, I believe it's October 13th, there are no classes. There are no night classes. So that night there won't be a class. Unfortunately, the way our schedule works out, this is the 22nd. We've got 2 more lectures in this unit, the 29th and the 6th. The 13th, that there's no classes, we'll come back from that night off on the 20th will be our second unit test. So you can look at it 2 ways. You got 2 weeks after that class to study for the test, or you've got 2 weeks after that class to forget everything before the test, whichever way you want to look at it. It's a floating in-service day. They have those in the middle of semesters to kind of even out the schedule. Otherwise, there'd be 17 Tuesdays. Do you really want an extra week of math class? Okay. 'Cause I'll take the extra week. I'm okay with that. So anyway, we've got these measures of center that we found. Like I said, the measures of center were the mean, median that we just looked at, and then there's another one, the mode, which is just the number that appears the most often, the most common number in the list. And we also talked about a mid-range, which was just taking the minimum and the maximum and averaging them together. And those are all trying to describe the center which remember data normally occurs in a bell curve like this called the normal curve. So we're trying to find the location of the middle of that curve, the center of that curve. On a good set of data, all of those will be the same number. Mean, median, mode, mid-range, all will be the same number. But we do have data that is what we call skewed left. Or skewed period. But we have skewed left would look like this. It's been stretched out to the left side. Now, in a set of data like that, the mode is at the highest point. Remember, that's the most commonly occurring number. That is the mode. The median gets pulled a little bit off center. But recall, the one that gets changed the most, we talked about that example with is it North Carolina University talking about their marketing graduates with Ralph Sampson. From him, those very, very extreme values can change the mean quite a bit. So if it's skewed left, it's stretched out way to the left like that, and the mean gets pulled out way to the left, and the median and the mode don't change quite as much. Or it can be skewed to the right, where it's stretched out way to the right, like this. And in that case, again, the mode is still the highest point. Pretend that's the highest point. The median gets moved a little bit, but it's the mean that gets moved the most. And I'm just matching them up by color there so I don't have to rewrite the words. You get the picture. I'm not going to test you on skewed or anything like that, but it's something that's good to know, that a good set of data, it doesn't matter which measure of center you use because they're all in the same spot. But the more skewed it is, the more questionable the mean becomes, because it's the one that gets affected the most. And then our measures of center. And for measures of center, the only ones we discussed were the range, which we found earlier, and the standard deviation. That's center. What am I talking? They're not measures of center, they're measures of spread or dispersion. Sorry about that. It might be one of those nights, so I'm misspeaking already. So we found the range and the standard deviation. And what those were talking about on that curve is the width of the curve. We can have a curve, still a bell curve, but it's very narrow. That has a very small spread or small dispersion. Or we could have a bell curve like this as more of a medium dispersion. Or we'd have one like this that's very, very spread out. Large spread, large dispersion. The range we said was not nearly as reliable because we could have sets with the same range with very, very different spreads. But the standard deviation was very, very good at determining between the spreads of different sets of data. Remember, the standard deviation is basically telling us what is the average distance of each point of data from the mean. Well, another way of setting up or breaking down a set of data is to talk about measures of position. I'm going to start out by talking about the one that you probably hear used the most, and that is percentiles. Percentiles measure basically, percentiles are used a lot on standardized tests. In high school, you may have taken the state tests or whatever, or when you were admitted to college, you may have taken an entrance test where they said you placed in a certain percentile. Let's say they say you placed in the 82nd percentile. What that is saying is that your score was equal to or better than 82% of all of the people that have ever taken that test. Oops. So I'm going to set up a set of data here, and we're going to work with percentiles a little bit. Let's just say that these are scores. I won't say of what. So what are that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we'll go a couple more. So there's a set of scores. Now the first thing we have to do for percentiles, just like with our median, is to put them in order. And generally, just like the median, we go smaller to largest. Smallest to largest, sorry, smaller to larger. Once we've done that, which I already did with this set, when I created it, I put them in order. The next thing we're looking at is finding a position for a particular percentile. And the position works exactly like it does with the median. So for example, find from this data set the number that represents the 30th percentile. So its position, instead of 0.5, however, we're going to use, what's the decimal for 30%? 0.3 times n. Well, what's n here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 numbers, so n equals 14. Now there's another reason why I numbered them out, because we're going to need them numbered. It's going to help us to have them numbered in a little bit anyway. So n equals 14, so the position of the 30th percentile is 0.3, the decimal of 30%, times 14, which is 4.2. Just like with the median, if it is a decimal, we round up. Never down. Even though it's 4.2, it rounds up to the 5th number in the list. So what that means, the 5th number in our list, here's 5, 51. So the 30th percentile is 51. So that score of 51 is the score for which 30% of the other numbers are below it. Now, because this is a relatively small set of data, there's a little quirk with it. Let's say I want to find the 35th percentile. Talk me through. What am I going to do? What's 35% as a decimal? 0.35 times 14, which is going to be 4.9, correct? Which is going to round up to the 5th number in the list. Well, the 5th number in the list is still 51. So the 35th percentile will also be 51. Because this is a small set of data, 51 is actually, what, anywhere from, it goes over a range of like 7 or 8% percentile. A larger set of data, the percentiles are more meaningful because each number is usually actually not only just a single percentile, it might even be a half or a quarter of a percentile. But because there's only 14 numbers here, each number is actually like 7.28% of the whole list. But anyway, let's keep trying. Let's find the 85th percentile. Now, if you guys try to find that before I do, wait a couple minutes for you. So 0.85 as a decimal is, or 85% as a decimal is 0.85, times n is 14, which is going to give us what? 11.9. So we're going to round up to the 12th position, which is 71. So the 85th percentile is 71. What if I ask you to find the 50th percentile? Well, what are we going to multiply by n here? 50% as a decimal is 0.5 times 14, which is 7. Now, since that is a whole number, that means it is between that one and the next one. So between the 7th and the 8th number. So that would be between 57 or 54 and 57. So 54 plus 57 is 111 divided by 2 is 55.5. Note, by the way, when we found the median, what did we multiply n by? 0.5. The 50th percentile is the median. Next, what if we want to know, if we pick a particular number in this list and we want to know what percentile it falls in? So let's say that your score was the 59, and you want to know what percentile that is. To find the percentile, find the percentile rank. The percentile is equal to the number that are smaller plus the number that are equal divided by 2, all over n, then multiplied by 100 to make it a percent. So for the 59, if I look up here, how many are smaller than the 59? 9 of them. So this is going to be 9 plus, how many are equal to 59? Only the 1. So that's going to be 1 divided by 2 over n, of course, is still 14. So 9 plus 1, well, 1 over 2 is 0.5, so it's 9.5 over 14, which divides out to be 0.679. Times 100 is 67.9. That's the 67.9 percentile. That's saying you scored at or better than 69 or 67.9% of the people who took that particular assessment. Now, just because it's the only number that appears more than once in my list, let's find the percentile rank for 57. So here's the 57s. How many are smaller than 57? There's 7 of them. And how many are equal? There's 2. So for 57, smaller, there's 7 of them. Plus, there's 2 that are equal. So that divided by 2 over n is still 14. So 2 divided by 2 is 1. 7 plus 1 is 8. 8 over 14, which divides out to be 0.5714286 approximately, or 57.1 percentile. So approximately the 57th percentile. So let's say your score comes back. Just look at what these means. Let's say your score comes back and they tell you you are in the 52nd percentile. Is that good or bad? Bad? Well, it depends on how everyone else did, yeah. But what it's saying is, 52nd percentile is still saying you did better than more than half of the people. Basically, you're average, middle of the road. So 52nd percentile is not bad. Remember, the 50th percentile means you are exactly in the middle of the pack. That is the median. It's if you had like the 13th percentile that you want to worry. Okay. So enough on percentiles. There's another set of measures of location or position called quartiles. Quartiles are actually very tightly related to the percentiles, but they're used because the percentiles break down the data into 100 pieces. Quartiles only break it down into 4 pieces. And our quartiles, if it's broken down into 4 pieces, we can get a really good look at how the data is distributed if you gain some experience with the numbers. Now, before we get into this, if we go to cut a board into 4 pieces, how many cuts do we need to make? Not 4. 3. 1, 2, 3. So a set of quartiles cut the data into 4 pieces, but there's only 3 of them because we only need 3 cuts. So this would be the first quarter here, the quartile 1. The second quartile is right there, which is also, by the way, the median. And then the third quartile. I abbreviate them Q1, Q2, and Q3. So I'm going to write out another set of data here. For you. So another set of data. Now I'm just going to go ahead and number these right now so I have my n. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So n equals 13 here. To find the first quartile, sometimes called the lower quartile. The first quartile is 25th percentile. Makes sense, right? Quarter, 25%. So for this data, its location is going to be 0.25 times 13. Or otherwise known as 3.25, which means it is the 4th number in the list, or 60. This is our first quartile. Second quartile. which I'll tell you flat out is almost never called the second quartile because it is also the median. Which, as we've seen, is the 50th percentile. So 0.5 times 13 is 6.5, which puts it at the 7th number, which, as we can see, is 64. So the median, or if you want to call it the second quartile, is 64. The third. Anybody need me to slow down? Okay, the third, or the upper quartile, is also the 75th percentile. So 0.75 times 13 is 9.75, which rounds up to the 10th position. Excuse me, which is the 71. So the 10th number in our list is 71. 71 is the third percentile, or third quartile. So we've split the data up into 4 equal pieces, into quartiles. Now if you look at this, you realize it's not totally equal because there's actually 3 here and only 2 in here. Technically the 64 is included in both that and that, but we're not going to get too uptight about that. So anyway, we've divided it into quartiles. There is another measure of spread or dispersion called the interquartile range. It's kind of a pain to use because you first have to find the quartiles to find it. The interquartile range, which from here on out will be called the IQR, is the third quartile minus the first quartile. So for this data, it would be 71 minus 60, which is 11. Now for this course, the detail we're going to go into statistics, the interquartile range is not overly useful to us. If you get into a deeper study of statistics, it is incredibly useful for you. Right now, what I'm going to talk about is a little bit of that more detailed. You don't have to put it in your notes because you're not going to be tested on it. But the interquartile range for this data is 11. The overall range for this data, well, we've got 42 to 97. So it's going to be 97 minus 42, which is 55. In a set of data that is evenly distributed, is spread out all nice and evenly, the interquartile range will be about half of the total range. Because remember, the interquartile range from the first quarter to the third quarter contains about half of the numbers. So if they're evenly spread out, that would be about half. In this case, the interquartile range is a lot smaller than half, which means the numbers are very tightly grouped in the center, which means we have more of a narrow curve. There's a lot of numbers in the center here and not so much out on the edges. If the interquartile range is about half of the range, that means our distribution looks pretty much like this, basically flat. So about half the data takes up half the range, and the rest of the data takes up the other half of the range on the outside edges. Very uncommon, but not impossible, is if the IQR, the interquartile range, is more than half the range. What that means is that the data is really spread out and probably what we call bimodal. I'll explain that in a second. Might look something like this, where it's humped up on the outside edges. So what it's saying is it takes a huge part of the range to get a quarter of the data, and then very little on the outside edges to get a huge part of the range in the middle to get half the data, and very little on the outside edges. where something like this would occur. For example, let's say you have a large test that maybe only have like 4 questions on it. I had some of those in college that only had like 3 or 4 questions. And they were still 2-hour tests, by the way. But let's say that this is the people that had all the questions right, or maybe only 1 wrong. And this is the people that had 2 wrong. And then partial credit, there are still some a little bit in between or whatever, and some above it. But there's a large hump right at those scores that correspond to exactly 1 or exactly 2 wrong. And there are other things in nature where that does occur too. If you're looking at animal populations, you look at populations that have 1 offspring versus 2 offspring per parent, per adult female per year. Like I said, this is more detailed than what we're going to go into in this course, but you can actually, if you get deeper into statistics, the simple thing like the interquartile range does tell you a lot about the distribution of the data. Well, it's a little bit early for our break right now, but I'm going to take our break, so let's go ahead and we'll come back at 6:25 for our 2nd hour lecture.